Hello everybody. Welcome to the fourth online module for ManEc 453. Today we're going to be discussing how to estimate betas in varying market conditions. Before we dive into the content of the module, let's again find ourselves in the map. You can see that right here we are on the fourth module, estimating risk-adjusted returns and exploring CAPM and Fama-French-Carhart models. We're going to be spending most of our time today on the capital asset pricing model. In particular, we'll be estimating betas in different market conditions. Brief reminder of the objectives of the Excel portion of ManEc 453. Today we're going to work on basic Excel functionality and also regression analysis. So that helps us locate ourselves in the map for the modules. Now let's go ahead and dive into the content. The goals for module number 4 are that we want to review the basics of CAPM and beta. We want to discuss some of the uses of beta and alpha. We want to explore the importance of estimating betas in different market conditions, and then we want to give you an opportunity to practice estimating betas in different market conditions. I know that everyone who's taking ManEc 453 has already been exposed to the capital asset pricing model in at least 2 previous classes, so I believe we can move very quickly through this, and it doesn't require any in-depth explanation, so I'm only going to give you a cursory review of the capital asset pricing model. Remember that for any asset, which I will just label the generic asset I, the expected return or the required return for that asset is the real rate of return plus the expected inflation premium plus a risk premium. The logic being that if you invest in any risky asset, you should at least earn whatever a riskless asset earns. That would be the real rate of return. You should also be compensated for inflation, and you should be compensated for the risk specific to the asset in which you are investing. Remember further that we often combine the real rate of return and the expected inflation premium to create the risk-free rate. So the risk-free rate is nothing more than the sum of those two components. Therefore, replacing those two components with the risk-free rate, we can redefine the expected rate of return for any asset to be the risk-free rate, which is again the expected return on a riskless asset plus the expected inflation premium, and we also have a risk premium. Moving forward, we know again that the expected return on any asset is the risk-free rate plus the risk premium. Logically, this risk premium should be whatever the premium is for bearing average amounts of risk scaled by the amount of risk present in asset I. So generally speaking, in order to estimate a risk premium, you start with the premium for bearing average risk, and then you scale that by the amount of risk that you have in the asset you are analyzing. The capital asset pricing model, which is a specific form of an asset pricing model, this is the generic form. The capital asset pricing model becomes a specific version of this generic form. The capital asset pricing model asserts that only systematic risk is rewarded. Remember, there are several types of risk. Systematic risk is the type of risk that cannot be diversified away. This is in contrast with unsystematic or idiosyncratic risk. Unsystematic, idiosyncratic, firm-specific risk, those all mean risks that could be diversified away. Systematic risk is the risk that cannot. The capital asset pricing model further asserts that systematic risk, the risk that cannot be diversified away, is best quantified by beta. Beta being the slope of a line that best fits a scatter plot of the market returns on the x-axis and the asset returns on the y-axis. So if you plotted the market returns on the x-axis and the asset returns on the y-axis, and you fit a line through those points on the scatter plot, beta would be the slope of that line. Mathematically, if we think of the asset being the y variable, and it's a function of the market returns, which are the x variable, so over here you have the asset returns as the y variable and the market returns as the x variable, then mathematically the beta of that y, or the beta of that asset, would be the covariance of the two variables. That's sigma xy, just means the covariance of the x and the y variable, divided by the variance of the x variable, which in this case would be the market. So to get the beta of an asset, for instance Walmart, you just take the covariance between Walmart and the market, and you divide it by the variance of the market. Average beta is 1, so assets with average systematic risk have a beta of 1. Therefore, if all of this holds, if the risk premium should be the premium for bearing average amounts of risk times the amount of risk present in asset I, and if all of these assertions related to the capital asset pricing model hold, then the appropriate risk premium should be the average risk premium multiplied by the beta. The average risk premium is also known as the equity or market risk premium. It's represented by the difference between the expected return on the market and the risk-free rate. The reason we take the difference between the expected return on the market and the risk-free rate is because the market portfolio is a perfectly diversified portfolio with a beta of 1. Therefore, the expected return on the market literally represents the return to a portfolio with perfectly average systematic risk. We subtract out the risk-free rate because we have already captured the risk-free rate earlier in the generic form of the asset pricing model here. So these are all the assertions of the capital asset pricing model. Only systematic risk is rewarded. It's quantified by beta. Beta is the covariance of the asset in the market over the variance of the market. An average beta would be 1. And so average risk premium would be the expected return on the market minus the risk-free rate. Therefore, in order to get the total risk premium, we would just take this average risk premium and scale it by the beta, which is the amount of systematic risk inherent in the asset. Putting all that together, we arrive at the capital asset pricing model, which says the expected return on an asset is the risk-free rate plus the average premium for bearing systematic risk, which is the equity risk premium, scaled by the amount of systematic risk inherent in the asset, which is represented by beta. And beta, again, is the covariance of the asset in the market divided by the variance of the market. We transform this into a functional model. We call it a single variable index model. It takes this form. You can see in the single variable index model what happens is you move the risk-free rate onto the left-hand side of the equation, and then all you do is go and get observations every day, week, month, or year. That's a user choice. Typical convention is to use monthly data. So what you would have is for your asset, you would have the return to that asset every month. You would have the risk-free rate every month. You would have the return to the market every month. You would have the return to the risk-free asset every month. So this right here, the return to the market minus the risk-free rate would represent your X variable. The return to your asset minus the risk-free rate would represent your Y variable. So we have Y equals alpha plus beta X. You would run a regression. If you ran a regression with this as your X variable, this is your Y variable, you would get 2 parameter estimates from the regression. You would get an alpha estimate and a beta estimate. This beta right here is a representation of the amount of systematic risk in the asset. Now, if the capital asset pricing model holds and if markets are efficient, we anticipate a 0 alpha. The reason for that is because we have moved the risk-free rate to the left-hand side of the equation. By moving the risk-free rate to the left-hand side of the equation, we expect that to be 0. If you get anything but 0 there, the most accurate interpretation is to say these are returns that have nothing to do with systematic risk. Oftentimes this alpha gets called abnormal returns. Fair enough, but the most accurate interpretation is to simply say alpha represents returns generated by the asset, not related to the risk-free rate, and also not related to systematic risk. So that's the capital asset pricing model. That is the single variable index model that is derived from the capital asset pricing model. What are some uses of the capital asset pricing model? Well, we use the complete capital asset pricing model to estimate the return that is expected from a particular asset. We also use it to estimate the cost of equity in corporate finance settings. We use the beta from the capital asset pricing model to estimate the amount of systematic risk present in a particular asset. We can also estimate the amount of systematic risk present in a portfolio. Closely related to that, we can also estimate the beta of a portfolio, which gives us some sense of how much of the fund manager's returns are actually just driven by movements in the market. It's very important to know that. A lot of managers like to brag about returns. However, they're chagrined to discover that most of their returns are just a function of the market going up. What we would really be keen to find out is if there are fund managers who can generate returns when the markets are going down. We use alpha to estimate the abnormal returns generated by a particular asset. And we also use alpha to give us an estimate of the abnormal returns generated by a portfolio manager. This gets back to the discussion just a second ago. We're worried about the beta of a fund manager. We want to know how much of the fund manager's returns are simply a function of the market. This alpha tells us how much of the fund manager's returns are not a function of the market. And so alpha, in many regards, is considered a measure of fund manager acumen. There are, however, obvious issues with CAPM, and these are only a smattering of the issues. Those of you who have been more fully exposed to the capital asset pricing model have a deeper understanding of issues that I'm not covering here. But here are some of the obvious issues. CAPM assumes a linear relationship between asset returns and market returns. There's absolutely nothing that says the relationship has to be linear. Also, the capital asset pricing model, generally speaking, over time assumes that beta is static, meaning it doesn't change. There's no reason why a beta can't change. Also, related to that, and these are actually two ways of saying the same thing, capital asset pricing model assumes that the beta is the same in different market conditions. That may not be the case. So you could have a relationship between asset returns and market returns that's nonlinear. You could have a changing beta over time, and you could have betas that change as market conditions change. In today's assignment, we're going to focus on this last issue, the fact that in different market conditions, beta could actually be different. So what we're going to do today is we're going to investigate whether or not betas can be different during different market conditions. Let me just give you a couple of examples to try to show you these issues with the capital asset pricing model. Example number one, consider the betas of the following stocks. Southwest Airlines, Apple, Home Depot, Walmart, and McDonald's. I'm using data from June 30th of 97 to June 30th of 2012, and I'm using Ken French's market minus the risk-free rate as the equity risk premium. And all I did is I calculated the beta using monthly data for these stocks over my sample period, but I calculated the beta in a variety of market settings. I calculated the beta only during up markets, I calculated the beta during down markets, and I calculated the beta during what I defined as extreme down markets. And you see some interesting things, but I wanted to focus on these two right here. Look at Walmart. During up markets, Walmart's beta is 0.77. During down markets, it's 0.29, and during extreme down markets, it has a beta of 0.18, which is approaching 0. McDonald's, on the other hand, has a beta of 0.31 during up markets, 0.85 during down markets, and 0.96 during extreme down markets. So think about what that means. That means that during a down market, let's look at just extreme down markets. So the market tanks on the downside. Walmart's beta, meaning you can think of that as its correlation with the market, goes to almost 0. So Walmart becomes a nice hedge during an extreme down market, at least historically. McDonald's, on the other hand, its beta goes almost to 1 during extreme down markets. So when the market starts to fall apart, McDonald's goes lockstep with the market. So if you're trying to create some sort of portfolio hedge to protect your portfolio against extreme downturns, clearly Walmart would be a better candidate to provide that hedge for your portfolio than McDonald's. What I want you to see is you can get very different betas during different market conditions, and that's something you wouldn't be able to see if you just ran a beta on the overall sample. Here's my second example of how the CAPM can break down. Consider a hedge fund manager that engages in a simple strategy. The only activity in this hedge fund is that the hedge fund manager continually writes deep out of the money put options on the S&P 500. So let's take 30 seconds and remind ourselves of what that means to write deep out of the money put options. Remember, a put option is the right but not the obligation to sell an asset at the exercise price. So if you write an S&P 500 put option that's deep out of the money, that means the exercise price is far below the level of the index. So when you write the option, you would get income, and you would only lose money if the options get exercised. And the options would only get exercised if the S&P 500 goes down considerably, since you've put the exercise price so low on the options. This is a very risky strategy. In other words, there's a huge amount of tail risk. Your income is going to look very constant no matter what the market's doing until the market tanks, at which point you're going to lose a lot of money. So let's look at the implications of this strategy. If the market is up, the options won't be exercised and you'll just have a steady stream of income. And that would mean if you ran a CAPM regression, During those periods, you would see a positive and significant alpha and a beta near zero. Think about why that is, because you're getting a steady stream of income regardless of what the market's doing. So you're going to get not much beta, and you are going to have positive and significant alpha because you've got good returns. If the market's not extremely up, but just up, again, the option's not exercised, you'd have steady income. You'd probably show a positive and significant alpha. Now you'd probably be getting a beta, it would be registering as significant, but it certainly wouldn't be one. So you would have positive and significant beta, but you would also have positive and significant alpha because, again, you're generating these returns that are highly uncorrelated with the market. If the market is flat, again, options not exercised, you're getting steady income. You're going to give a positive and significant alpha and a beta near zero because you're not having any correlation with what's happening in the market. And the same would hold if the market is down. If the market is down, you're just going to have this steady stream of income. The options aren't exercised, positive and significant alpha, and a near zero beta. So what I want you to see is if you ran a CAPM regression, most of the time the market is either down, flat, up, or extremely up. Actually, most of the time it's down, flat, or up. So if you ran a CAPM regression, what you're going to get is positive and significant alpha and a beta that's probably near zero, maybe slightly positive, but it's going to look, generally speaking, as if this guy is some sort of superstar. He's creating a lot of positive, significant alpha, and there's not a lot of beta. But here's the deal. If the market ever tanks, those options will be exercised. The portfolio will be absolutely decimated. There's going to be huge negative and significant alpha, and the beta will shoot above 1. But the problem is we see so few of those episodes in a data set that all of these data points will overwhelm this data point, and you're going to get a CAPM regression. If you just do an overall regression, that's probably going to show positive and significant alpha, and it's probably going to show a pretty low beta. So what's the conclusion from these two examples? It's really beneficial to estimate alpha and beta under a variety of market conditions. In other words, the only way to see this, the only way to discover these shenanigans that might be played by a fund manager is to actually isolate these different market conditions. Run a regression during up conditions, run a regression during down conditions, run a regression during extreme down conditions, which is exactly what I did here. And you can see that you get very different results, and this is just with individual stocks. So the moral of the story is you need to estimate those alphas and betas under a variety of market conditions. It can aid in managing the systematic risk of a portfolio. So if you're looking at what stocks to invest in, it can help you pick out which stocks might help you avoid catastrophic events in the portfolio. It can also help aid in detecting managerial acumen. So for instance, if you see a high beta in an up market and a low beta positive alpha in a down market, that's a sign of pretty good managerial skill. If you see the opposite, if you see high betas in down markets and low betas in up markets, that's not a sign of managerial acumen. And it can also aid in detecting risky strategies like what I just showed you previously. If you see extreme high betas in down or extreme down markets, that's something you want to watch out for. Now this recommendation to estimate your alpha and your beta under a variety of market conditions, this holds for multi-factor models as well. Many of you have been exposed to the Fama-French 3-factor model and the Carhart 4-factor model. There's no reason why you can't estimate those models in up and down markets and see if the alphas and the betas are different. What you'd really love to see are high betas during up markets and high alphas during down markets. Now let's talk about what the assignment will be associated with this fourth module. Our goal is going to be to investigate managerial acumen by estimating CAPM betas and just a few alphas under a variety of market conditions for 4 different mutual funds. What you're going to do is you're going to look at up market, down market, and extreme down market. Those are the 3 conditions. And you're going to do it for the following mutual funds: BPLSX, GABCX, MERFX, NCHPX. You're going to use monthly data from June 30th of 2002 to June 30th of 2012. You'll use Ken French's market minus the risk-free rate as the equity risk premium. And you're going to estimate alphas under each of those same conditions only for the mutual fund with the lowest beta and the extreme down markets. Let me show you how to do this for a different set of mutual funds and over a different time period, and you'll recreate it for the mutual funds in the time period that you see here on this PowerPoint slide. I'm going to do this for the following mutual funds: FMLSX, ALPHX, POPAX, and BUFOX. I'm going to use a narrower time period than you. I'm going to start June 30th of 2004, and I'm going to end June 30th of 2012, and I'm going to use that time period for all of them. And then remember, this is just a macro that we've previously made available to you. If you view the macro, run it, it will scrape Finance Yahoo and bring in data for all of the mutual funds. Let me just make sure I have data all the way down to June for all of these, and I do. So then what I'm going to do is I'm just going to create a new tab here, and I'm just going to highlight all of these dates here, bring it up. And look, you could automate some of this. I'm just going to do it the fastest way just to get it done. So I'm just going to copy and paste over the closing prices for all of these mutual funds in each of those months. So again, forgive me, you could automate some of this, but I'm just going to do it as fast as I can to be done with it. So I'm just going to highlight that and copy it. Then I'm going to highlight that and copy it. And then I'll go get it for this mutual fund. Copy it, and lastly for this mutual fund, and there we have it. Now what we're going to need for all this is we're going to need the returns, and so before I do that, actually I'm going to sort this from oldest month to newest month. So I'm just going to highlight it, and I'm just going to sort it based on date from oldest to newest. It looks like that. I'm going to just copy these labels over, and now I'm going to calculate the returns using continuously compounded returns. So it's just the log of the ratio, right? The ratio of this month's price divided by previous month's price. I'm going to do that, send it on down, copy and paste that over, and I'm just going to turn all these into percents and give it a few decimal places and center it. Once we've done that, we can hide the prices because we have the returns. Now what we need is the risk-free rate, because if you remember, what we need to estimate this single index model. And in order to estimate the single index model, the y variable is going to be the return to the asset every month minus the risk-free rate. The x variable will be return to the market minus the risk-free rate. So we need this risk-free rate to get our y variable. In order to get the risk-free rate, I'm going to get it from Ken French's data library. If you just go to Google, type in Ken French data, it's the very first option that pulls up. The page looks like this. If you just scroll down a little bit, you will see the Fama French factors right there. If you open it up, all you have to do is take that file, copy it, and then go paste it or save it wherever you want to put it. So for me, I'll just go and put it here in the same folder. In the fourth Excel module, I paste it in, and there you can see the Fama French research data factors. Once you've saved it into your folder, just go back to Excel and open it up. You might have to, right here, it might be on all Excel files, you might have to change that to all files. Click on the Fama French research factors, and you can just click through the wizard, hit finish, and it will pull up the way you want it. Now, one thing to keep in mind, these are all in integer format. In order to turn them into decimals, you need to divide them by 100. That's not hard. All we're going to do is we're going to pull these in, and we're going to divide them by 100. But in order to pull them in, please notice that the date format in this file is different than the date format in this file. Over here we have standard Excel date format. Over here we have the Fama French research format. So you have to make those compatible. One way to make them compatible, let me just give you a demonstration here. One way to make them compatible is this. Take the year of this Excel date, multiply it by 100, and then add the month of the Excel date. So if you take the year of the Excel date times 100 plus the month of the Excel date, you can see it turns into the exact same format. In other words, it's the year followed by the month, which is the way that it's formatted over in the Fama French document. So I'm going to do this all in one step. So let's just try to make this as clean as we can. What I'm going to do is a VLOOKUP, and what I want to do is I want to look up this date over in the FAMA French data table and then pull in the corresponding risk-free rate. But remember, the date formats have to be compatible. So before I tell it what date I'm looking up, I've got to make it compatible. So what I'm going to do is I'm going to look up the year of A3 times 100 plus the month of A3. So all that's saying to Excel is, okay, you're going to do a VLOOKUP, and the date you're going to look up is this thing right here, but I'm putting it into the FAMA French format. So that's what I want to look up. I'm going to look it up in this document right here. I'm going to highlight the whole table, and you can see the risk-free rate is in the 5th column. So highlight the whole table, and then the next thing you need to tell Excel is what column. It's the 5th column, and then I'm going to do false because I want an exact match. Now remember, we have to divide that by 100 because it's not in integer format. So there's the formula. VLOOKUP, year of our date times 100 plus month of our date, then go over to the FAMA French data table, tell it it's the 5th column, false meaning we want an exact match, divide it by 100, now you got your risk-free rate. Shoot it on down the line. Now what we want to do is we want to take, again, all of these mutual fund returns minus the risk-free rate. So I'm going to do something real quick here. I'm just going to do concatenate, and I'm going to concatenate that with minus RF, like so. And you can see that's just giving me the labels that I want. The concatenate function just simply takes two things and sticks it together. So I'm just taking that text and sticking it together with minus the risk-free rate. So let's go ahead and do that. Let's take the return to BUFOX minus the risk-free rate. I'm going to lock in the J column. That way I'll be able to drag this formula around. So that's how we get our Y variable for that mutual fund. So that right there represents the return to this mutual fund every month minus the risk-free rate. When we estimate the single index model for that mutual fund, that's going to be the Y variable. Want to do the same thing for all of my mutual funds? I can copy and paste the formula over because I locked in J. Now we have the Y variable for all of our mutual funds. Now the only thing we need is the X variable. So we need the market minus the risk-free rate. That's going to be our X variable. So the return to the asset minus the risk-free rate is Y. Return to the market minus the risk-free rate is the X variable. Ken French has already calculated this for us. You can see market minus risk-free rate for every month. So I'm going to use that same VLOOKUP function, year of A3 times 100 plus month of A3. I'm going to look it up in the FAMA French table. I only need 2 columns this time. Again, I'm going to tell it false to give me an exact match. I'm going to make sure it works, and then I'm going to divide it by 100 because we got to get it in decimal format. Shoot that all the way down the line, and now we have everything that we need to proceed. I'm going to hide all this because we don't need it. I'm going to do 2 other things. If you go to the very bottom, you'll notice that there's a last row that we don't need. You might as well delete it. I'm also going to highlight all of this data. I'm going to copy it, and I'm going to do paste special values only. So once I've calculated all these returns, once I have my X and my Y variable, I'm going to make it so that there are no formulas on this spreadsheet. I normally would not advise doing that. We like formulas. We like our spreadsheets to be dynamic. But in this case, we have to get rid of the formulas. Otherwise, we'll run into huge problems as we start doing some sorts later on. I'm going to click OK, and you can see that now the formulas are gone. And I'm going to get rid of this row that doesn't have a return in it. That was just the first month that we needed in order to calculate returns. So now we have our data table, and we're ready to rock and roll. What I want to do is I'm just going to copy and paste these labels over. We're going to calculate the average return, the standard deviation, and the beta just under normal market conditions. So let's do the average of this mutual fund minus the risk-free rate. We can copy and paste that formula over. Let's do the standard deviation. So that's the standard, and I'm going to do the standard deviation of a population. You're going to want to do that if you're going to shortcut beta, and we are going to shortcut beta. So I'm going to do the standard deviation of a population. I'm going to do that for all of them, and we'll turn all of those into percents with 3 decimals, and we'll center them. Now what I want to do is I want to shortcut the beta. I don't want to have to run 5 regressions. Let's just shortcut beta and see what it looks like. So remember, beta is the covariance. Remember, beta is the covariance between the x and the y variable over the variance of the x variable. So what we would want is the covariance, again, of a population. For this mutual fund, that would be the first variable. The second variable would be our x variable, which is the market minus the risk-free rate. So we have the covariance, and we need to divide it by the variance of the x variable, which is our market minus our risk-free rate. Well, there's the standard deviation. If we just square that, that's going to give us our variance. So covariance between this variable and this variable divided by the variance of this variable gives us beta. We're going to turn that into general format, and I'm going to lock in the O's and the V's. Why I'm doing that is because if I lock in this column and this column, I can drag this formula across and shortcut all the betas. Now we can tell that we did it right because the beta is 1. That's exactly what you would expect. The beta for the market is 1. And you can see that these mutual funds have very different betas. Okay? This one has a beta of 1.44. This one has a beta of 0.43. Now what I'd like to do is just see how this looks in up markets, down markets, and extreme down markets. And we want the same thing. We want the mean, the standard deviation, and the beta. So in order to do this, what we have to do is we have to resort the data, and we're going to sort it based on what's happening in the market. So we'll do this. We'll highlight it, we'll sort it, and we'll sort it based on the market from smallest to largest. So let's start with the up market, and you can see that the up market starts right here in August of 2004. So let's get the average for each of the mutual funds starting in that month. And we'll copy and paste it across. Let's get the standard deviation of a population, again, starting in that month. And also copy and paste that across. And turn all of it into percents. And center it. Now let's go ahead and calculate the betas. So covariance of a population, again, we're starting in the first month that we get positive market returns. So the covariance of that mutual fund, and with the market starting in that month, and we need to divide it by the variance of the market. There's the standard deviation. We square it. We lock in the O's, lock in the V's. Give it a little bit of formatting help. And do a little bit of cursory analysis here at the beginning. So during up markets, it looks like generally speaking, most of the betas are going down. Not necessarily what you'd love to see, right? During an up market, we'd love to have really high betas load up on the market during an up market. Let's see what it looks like during down markets. So again, I'm going to calculate the average. But now I'm going to do it during down markets. So down there, copy and paste it across. Let's get the standard deviation of a population down to right there. Copy and paste across, give it a little bit of formatting help. And now let's calculate the betas again. So covariance of a population, now we're going down to here. And we want to line that up with the market. We want to divide it by the variance of the market. And we want to lock in the O's and the V's. Slide it across, give it a little bit of formatting help, and there we have it. So what do we see? Generally speaking, we see that during down markets, the betas are higher than they are during up markets. That's a little bit disconcerting. That means as the market goes down, we start to trend more closely with the market. And now I'm interested to see what it looks like during extreme down markets. Now, there are a variety of ways that you could try to define extreme down markets. The trade-off is this. We would like it to truly be extreme. Like right there, we can see those are clearly extreme down markets. The market's going down 4% in a month or more. The problem is that's only 15 observations. You really can't trust a beta that's estimated from 15 observations. So the trade-off is you want to get as many observations as possible while still at least loosely defining it as extreme down markets. In our case, in order to try to get as many observations as we can and still retain that definition of an extreme down market, why don't we call an extreme down market anything that's got more than 1.5% loss in the month? Let's do that. So let's get the average from there down to that month right there. Let's get the standard deviation over the same time period, over the same months, I should say. So down to there. And just format it a little bit. And now let's calculate the betas. So the covariance of that down to right there with the market over the same period divided by the standard deviation squared. Lock in the O, lock in the V, and give it a little bit of formatting help. So what observations do we make? And I'm really interested to compare up markets versus extreme down markets. And we want to see what you'd really love is a manager that during up markets does load up on beta and during extreme down markets has a very low beta. So let's take a peek here. You can see that this particular mutual fund, the beta goes up considerably during extreme down markets, considerably during extreme down markets, considerably during extreme down markets. This is the only mutual fund out of the four that seems to have a very consistent beta, whether it's an up market or an extreme down market. Whatever that mutual fund is doing, they have a strategy that's consistent, regardless of what's happening in the market. So why don't we investigate this mutual fund a little bit more? In particular, I'm interested to see if this mutual fund is generating any alpha. They have a moderate beta, but the beta is consistent regardless of what's going on in the market, and that's interesting to me. So what I'd like to do is just run two regressions. I want to run a regression where we look at their alpha during an up market and their alpha during extreme down market. So this is our betas, and now what I want to do is run some regressions. So since we have a mutual fund that has a pretty steady beta, it doesn't have a beta that's skyrocketing during these extreme market downturns. I'm interested to see if this particular mutual fund generates alpha. So let's go ahead and estimate those two regressions, regression during up markets and regression during down markets. And to do that, we'll go ahead and do the traditional method of just going to the Data tab, Data Analysis, choosing the regression option. And the mutual fund we're interested in exploring is this FMLSX. So during up markets, that will be the first regression that I want to run. And again, we have to locate right here is where the up markets begin. And so let's highlight all of that. And then for the X variable, it will be the column right next to it. And let's go ahead and have this generate a new worksheet for us. Click OK and take just a minute to analyze what we see here. So there's the beta that we calculated, and this is probably a worthwhile exercise just for you to be able to demonstrate and get comfortable with the fact that we are calculating beta the right way. You can see during up markets we arrived at a beta of 0.71 for this mutual fund, and that's what you get when you run the regression. Interestingly enough, the intercept, which you want to turn into a percentage, interestingly enough, the intercept is negative and the p-value is pretty high, which suggests that there's actually no alpha. So even though it's negative, you have a high p-value. Remember, the p-value represents the probability that you could get an outcome this extreme in a sample if the true value in the population was 0. So even if the true value in the population was 0, you have a 41% chance of getting something like that in a sample. Another way to interpret that is simply there's a good chance that the actual alpha is 0. So we have a beta of 0.71 with this mutual fund, not much of an alpha. What I'm really interested in is to run a regression. So this is FMLSX alpha up. Now what I want to do is alpha on the extreme down. So I want to see how this particular mutual fund does in extreme down markets. So we're going to run the regression again, data, regression. But now I'm just going to go and pick the extreme down markets. There's the Y variable, the X variables in the column right next to it, going down to right there. Now, the same caveat holds here that we talked about earlier. This is a very small sample size. You're not going to get a ton of statistical power. It might not be terribly reliable, but still at least worth a peek. So we run it, and there's that consistent beta that we already knew about. And there's the alpha, which is positive 0.49, but the p-value is again 46%. Sorry to be a broken record, but remember, p-value is the probability of getting something that extreme in the sample if the true population value was 0. So if the true population alpha was 0, there's a 46% chance that we could get something like that in the sample. The alternative interpretation is the alpha is probably 0. So this is the FMLSX alpha in the extreme down markets. Okay, so let's just review real quickly what we've done so far, and then what we'll do is a little bit of formatting. I'll have you do one chart, and we'll be done with this assignment. So what we did is we grabbed 4 mutual funds. We ran some CAPM regressions to see what the betas were. Those were the betas. But then we wanted to see how these betas change during up and down markets. During up markets, for the most part, the betas are lower than the overall betas. During down markets, the betas seem to be up a little bit. And you can see that for the most part, the up betas are lower than the down betas. That's not something that's pleasing for us as investors. You'd rather see betas higher during up markets than down markets. And then in the extreme down markets, we actually see some really significantly high betas, 1.45 for that particular mutual fund. So during extreme down markets, that thing really has trouble. Interestingly enough, this mutual fund right here that has a pretty low overall beta, very low beta during up markets, starts approaching 1 during extreme down markets. This is the only mutual fund that seemed to have a really consistent beta, whether it was an up market, down market, or extreme down market. We got a pretty consistent beta. So we thought we would check for some alpha. During the up markets, we saw a negative but not statistically significant alpha. So we would call that alpha 0 with that steady and consistent beta. We also checked for alpha during the extreme down markets. We see it's positive but not statistically significant, and we see that steady beta. So what we can say is that this is a mutual fund that has a very steady beta below 1, basically generates no alpha. The last thing I'd like you to do for this assignment is just give it some formatting attention. And don't worry too much about the formatting on the regressions. Just make sure that you've got the important stuff highlighted, which would be the fact that we were testing for alpha. So just make sure those are highlighted. There's our beta. Now the last thing I want to do is I just want to create the chart similar to what you saw over in the PowerPoint slide, doing a beta comparison during up, down, and extreme down markets. So I'm going to come up here. I'm going to insert a column chart that's going to allow us to do comparisons. Let me slide that down so I can see what I need to. Right click on it. We're going to select data. And what we're going to do is this. We're going to say, first off, let's look at up markets. And we'll just highlight all of these betas right here. Let's look at down markets. And we'll highlight all of these betas right here. And then let's do one more, which would be the extreme down markets. And let's highlight all of these betas right here. And let's make sure we get the x-axis labeled appropriately. So we'll just highlight all of these right here for the x-axis, like so. Move this chart to its own location, so we'll give it its own tab. And we'll call this the beta comparison. And I'm not so concerned about whether or not you do any more color formatting. Feel free to do what you want, but your chart at least needs to look like this. And you definitely should label it. I think it's important to label charts. So you might want to do something like this that will allow you to label it. And just say this is our beta comparison. This is the beta. And this is the different mutual funds. And you can see quite clearly, here's a fund that during up markets has a pretty low beta, but then as the market gets worse, its beta starts to shoot up. So that's not going to be a great investment during an extreme down market. Here's the mutual fund that we investigated, just a nice steady beta, whether the market's up, down, or extreme down. So this chart, very easy to interpret, and it summarizes a lot of what we did right here. So those are the deliverables. You should have this beta comparison data tab. You should have a beta comparison chart tab, and then I want 2 regressions trying to see if there's any Jensen's alpha related to the best mutual fund that you see in your data set. Now, the way I picked my best mutual fund is that this had the most consistent beta across the different market conditions. For you, maybe you're going to find a mutual fund that has a lower beta in down markets. That would be really impressive, and that would be the fund that you would want to investigate yourselves. So that's Excel module number 4. As always, you can contact your TAs or your professor for guidance, and we'll see you in module number 5.